Hi, everybody. It's my pleasure to host Steve Croft for a virtual CFPU seminar this week. So Steve is at UC Berkeley in the SETI Institute and has graciously agreed to call in and tell us about his work with Breakthrough Listen. So I think, please go ahead, interrupt with questions. Steve said that would be great if anything comes up during the talk, and we'll leave some time for questions at the end as well. All right. Thanks, Steve. Go ahead. Take it away.
Great. Thanks, Johnny. Thanks for the invitation to speak. Do hope sort of when things return to normal that we'll have the chance to meet some of you in person, either out there or in Berkeley. We're always happy to have visitors come through the lab. And if you have ideas about ways that we might collaborate as well, then please do reach out to me. We have sort of broad collaborations with academia and with industry, and be happy to chat. So we've learned in recent years that planets are common around stars elsewhere in our galaxy, and indeed probably 1 in 5 stars has an Earth-like planet in the habitable zone of its star. So out of the hundreds of billions of stars in the Milky Way, there are maybe tens of billions of habitable planets that might be good places to look for life. And so, to sort of paraphrase Enrico Fermi in the Fermi paradox, which of course is not actually really a true paradox, but sort of still a puzzle, where is everybody? If there is life out there, and really sort of the history of astronomy shows us that, excuse me, when we thought, every time we thought that we were sort of in a privileged place in the universe, sort of the Copernican principle basically has told us that actually we're fairly average. So is there some sort of selection bias that is sort of privileging us as observers as we're looking out and seeing apparently sort of an otherwise, aside from Earth, an otherwise lifeless cosmos? Or are there other minds out there that have arisen, and might we be able to actually do a scientific experiment to look for them? So the field of astrobiology has really sort of blossomed in part over the last few years due to this realization that habitable planets are everywhere. And of course, as many of you know, Mars exploration has been a focus for NASA. There's a probe here. This is a rendering of the Perseverance rover, which is due to enter the Martian atmosphere tomorrow. So sort of pretty topical in terms of sort of investigations in astrobiology. And this is really one of the first.
Oh, sorry to interrupt.
Yeah.
We're still seeing your title slide. Should we be seeing something different?
You should indeed. So I'm not sure what's happening there.
Yeah, maybe quit screen share and start again. It was working.
That's good. Warming up on that. Okay, are you seeing an image of the Milky Way? You're still seeing the title slide?
Neither. Now it just says you've started screen sharing. So we did test this, promise.
Let me see if I can try. I've got 2 screens here, so let me just try them on a different screen. Let's see if that makes any difference. How about now?
No, it's the same as before. It just says you've started screen sharing.
Let me try sharing the whole desktop. You see that?
No, still says just started sharing. Somebody else should speak up if they're seeing something different than me, but yeah, it was working great about 10 minutes ago. So
well, it seems to work now. I can see you and some pictures on the wall behind you.
Yeah, unfortunately, you should be seeing, well, not right now, seeing my slides, but I would like to be able to share my slides with you. Let me try one more time. Anything
Okay,
more?
now we see the title slide and it's progressing. So
Yes,
we're all set.
Not sure what happened there, but okay. Great.
Thanks.
Yeah, so Milky Way is Enrico Fermi, where is everybody? And then the Perseverance lander, which is due to land on Mars tomorrow. So this is really, I think, sort of the way that I would break things up in terms of astrobiology is really three main techniques that we can use. One is this in situ sampling, where we can go there and actually sort of sniff the dirt and look for life. The other is remote sensing for biosignatures. So obviously getting to interstellar distances that are sort of at a minimum tens of thousands of times interplanetary distances that we can reach within our own solar system is very challenging. So doing these remote sensing measurements of the atmospheres of exoplanets is another way to search for life and specifically to search for biosignatures. And so these are indicators that there might be some sort of biology on planets around other stars. And you can see here some infrared spectra of Venus, Earth, and Mars in our own solar system. We don't expect anything like this sort of fidelity, even with the next generation of instruments that will be able to image the atmospheres or sense the atmospheres of Earth-like exoplanets. But there's a possibility that with some proposed missions in the sort of 2030s and 2040s, that we might be able to get some hints of things like, well, here it's showing water vapor and ozone or other compounds in the atmospheres of exoplanets that might be indicative of biology. But it's quite a challenging measurement to make. Even with these next generation of instruments, it's only going to be possible for a handful of nearby systems. And also, it's a little ambiguous in terms of sort of whether the signals that you're seeing are actually from biology. There was a claim, many of you will be aware of phosphine in the atmosphere of Venus recently, which I think a lot of people are still sort of pretty skeptical about, just in terms of sort of the processing that was done to sort of tease that signal out. It's possible that ends up holding up, but it's also possible that it goes away. And so sort of these measurements are really challenging to make. The third leg of astrobiology, in my mind, is technosignatures. And so this is sort of, again, taking the one example here that we know of biology here on Earth, which ultimately developed intelligence, which ultimately developed technology. Some of this technology, which is detectable at interstellar distances, even sort of under not particularly optimistic assumptions. Some of our most powerful radio transmitters, such as, well, the now defunct Arecibo planetary radar, could be detected at hundreds of light years of distance if it was pointed in the right direction and being received by a similar dish on the other end. And then the question is, could there be more powerful transmitters out there that we might be able to pick up? Might we be able to pick up sort of unintentional transmissions, the so-called leakage radiation that any civilization like ours generates just in terms of sort of radio waves going out into space? Or might there be lasers or other optical communications? Might there be large structures that we're able to detect that are out there? And so, it's sort of an open-ended question as to whether there's other intelligence out there. It's an open-ended question as to whether intelligence out there might have technology like our own, and then whether we might be able to detect it. But it's worth investing some time and energy and money in actually doing these searches, because we can sort of sit here and talk about this, or we can actually go out and try and put some upper limits on the prevalence of some of these technologies, or even optimistically, again, make a detection. So in 2015, the Breakthrough Listen initiative was launched at the Royal Society in London by Yuri Milner, who is the sponsor of the Breakthrough Initiatives and specifically the Breakthrough Listen program. And they pledged $100 million over 10 years to really revitalize the field of SETI, the search for extraterrestrial intelligence, or the search for technosignatures. We had a lot of media interest at the time. My boss, our director, Andrew Simeon, had a lot of media requests that he was triaging. So I think he maybe didn't want to do Fox business. I guess they were sort of excited about the $100 million figure. And I was sort of put out to go and talk to them about what we were going to be doing. So it's going to be an interesting interview. But to get a little bit sort of more in depth than I was able to do with the folks at Fox Business News, I wanted to sort of tell you a little bit today about how we've actually been implementing this search. So this is the Green Bank Telescope, 100-meter diameter steerable dish in Green Bank, West Virginia. It's the largest steerable dish in the world. And you can see here in the foreground, it's our chief engineer, Dave McMahon, for Breakthrough Listen. And Dave has really been responsible for a lot of the digital instrumentation that has gone out to not just Green Bank, but to our other sites that we're operating at around the world. We've also purchased 20% of the observing time on the Green Bank Telescope. And so we have sort of a robust observing program there, and at the other facilities that we're using that is making observations of several different samples that I'm going to tell you a little bit about, and I'll also sort of tell you a little bit about how we actually do this radio technosignature search. We have a similar instrument down at the Parkes telescope in Australia. Again, you see Dave and some of the other team, the Berkeley team and some of the local team there at Parkes, just after they installed the instrument there. And then we have some pilot programs and some other collaborations with other telescopes around the world, including, I know there's some folks working on NWA there. We have one of these servers, again, sort of similar to the boxes that we deployed to Green Bank and Parkes, which is sitting at Curtin University in Western Australia. And we're working with the folks there in part as well, sort of collaborating with them as part of the MWA Phase 3 upgrades, where they're replacing the correlator, and the correlator will be a lot more capable and really able to sort of do particularly the fine frequency resolution spectroscopy that we need to really do the kind of SETI searches that we want to do. We also have collaborations with LOFAR in the Northern Hemisphere, including the Ireland and Sweden stations with Jodrell Bank. We have a program that's starting up with SRT. And then really sort of one of the big ones is MeerKAT, where we're deploying an even bigger cluster than what we have right now on Green Bank out to the MeerKAT site, which is going to do commensal observing, in other words, sort of piggybacking on the observations that are going on from the main key science projects there at MeerKAT. I should also mention optical searches. The automated planet finder is doing some spectroscopy, looking for laser lines. VERITAS is looking for short flashes. VERITAS is a gamma ray Cherenkov telescope, so it's designed to pick up Cherenkov light from gamma rays that are in the upper atmosphere, but ultimately it's a big optical light bucket, and so we're using this to look for any bright flashes that might be detectable. So I wanted to just sort of switch gears a little bit and tell you a little bit about a collaboration that we have with folks at the GNU Radio collaboration. So GNU Radio, for those of you who are unfamiliar, is a really kind of fun way to just get hands-on with radio techniques. You can actually do some radio observations with this. There's a couple of projects out there that are building telescopes that are detecting hydrogen in the galaxy just from a simple horn antenna hooked up to one of these software-defined radio kits. And you can see in this sort of screen grab of the shop site on the left here, for $20 or $30, you can buy one of these devices, plugs into a USB port. They're originally designed for picking up over-the-air TV transmissions, but then folks realized that they could sort of hack them and actually sort of process the radio signals that come through these in various ways. Typically come with a little antenna, but you can sort of scale these up as more kind of high-end versions of these, and you can plug them into to bigger antennas. And so we basically have sort of a higher-end version of this that's out at the Allen Telescope Array in Northern California. And you can see a photograph from a hackathon that we held up at the ATA here with a bunch of folks from the GNU Radio Consortium, where they're taking the signals from these dishes and they're digitizing them and then processing them in sort of regular computing hardware. And we had a summer intern, Ellie White, who was helping us implement this at the ATA last summer. And then since then, the GNU Radio Consortium has now actually sort of come under the umbrella of the SETI Institute. The SETI Institute is helping them with grant applications and with sort of grant management and general sort of office functions, but also kind of helping promote GNU Radio, both as a teaching tool and also as a research tool in radio astronomy. So if you haven't sort of heard much about GNU Radio, but if you're interested, again, feel free to reach out or to go and investigate. There's quite a bit of stuff that's out there online. So if you fire up the software, there's some free software that you can get with GNU Radio. This is an example of a screen grab from some software called GQRX. And I'm picking up here our local NPR radio station, KQED 88.5 megahertz. And you can see in the top plot here, this is just a 1D sort of snapshot in time of the FM signal that's in this little band that's being picked up here. And then off to either side of this, in the sidebands here, are what we call the HD radio signal, the digital radio signal that if you're in a car, for example, with sort of a more recent FM radio receiver, then often you'll see it sort of switch to HD. It'll pick up more like a CD quality sound because this is digital radio that's coming in digital form in these sidebands. If you look down below this 1D plot, you'll see a 2D plot here. And if I had sort of a live demo, which I'm not going to try here over Zoom, but if I had a live demo, then you would not only hear the FM radio being decoded coming out of the speaker, but you'd also see scrolling down the screen. This same signal that is snapshotted in time here will be scrolling down the screen in time, sort of scrolling off the bottom, these sort of colored signals down at the bottom here. And you see the FM signal again here in the middle, and FM, of course, standing for frequency modulation. And you can actually see visually here, again, the frequency axis is the horizontal axis here, and then time is running down on the vertical axis in this colored plot down at the bottom here. And you can actually see the frequencies being modulated. If you look closely, you can also see that this is a stereo FM signal as the sort of two signals here that contribute to the stereo signal coming in here. And this is the signal that's being decoded by the FM demodulator and giving us the sound that's coming over the radio waves. And then again, if you look off to the side, here you'll see these digital sidebands. They just look, I mean, essentially like noise here. And this is an example of Shannon's theorem, the fact that if you put a lot of information, sort of maximally encode information in the available bandwidth that you have, then it will look like noise. But again, if you decode this using the correct decoder, then you're going to get a high quality digital signal coming out of here. So this is an example of a waterfall plot, so-called, because again, if you saw this sort of as an animated graphic, you'd see this scrolling up the bottom of the screen like a waterfall, where the most recent water is up at the top, and then the water that sort of came over the waterfall a while back is scrolling off the bottom. And again, just to emphasize, this is frequency on the horizontal axis and time on the vertical axis, and then the intensity of the signal that's being picked up from the antenna and then passes through the digitization step as the color scheme here. So we take the raw voltages from the antenna, we do a fast Fourier transform to get this waterfall or dynamic spectrum or spectrogram. These terms are sort of used interchangeably out here. And this is essentially sort of the bread and butter of a radio SETI search, and actually the bread and butter of the instrument that we have at Green Bank. So instead of the $20 dongle, we've scaled this up to a couple of $100,000 of high performance computing, which consists of just fast, off-the-shelf computer servers with a lot of hard drives with some GPUs in there, and with a fast network connection. And this is basically ingesting just a much larger bandwidth, doing these FFTs to get high frequency resolution that we need for the SETI search. And then we're looking through these waterfall plots, processing them automatically and looking for signals. And you can see here, you know, again, in the waterfall plot, the artificial signals are pretty clear. You don't need actually to be able to decode this as an FM signal to really recognize that there is some artificial signal here. You can see sort of these sharp edges of the digital signal that again sort of mark this out as something that's interesting and very likely artificial. And so finding artificial signals in radio observations is actually not really the major challenge that we face. And I'll get onto what the challenges are in the next couple of slides. So again, we sort of scale this up from this little antenna up to the 100-meter Green Bank telescope. So up at the top of the telescope here, you can see the secondary reflector, which is seen in close-up here. This is actually the prime focus feed that is on an arm in front of the secondary reflector. And so you can just feed in the signals directly from the dish into prime focus at the certain sort of frequencies that you're interested in here. Or you can swing that arm out of the way, and then it reflects down to this platform here, which has the feeds on this sort of rotating disc here, basically, that you can pull these into focus. We actually have a couple of videos on the Berkeley SETI YouTube where you can actually pan around. This is in sort of 360 VR where you can actually go and sort of ride the elevator up with us up to this platform and look down at the telescope. And it's sort of a nice way, particularly if you have like Google Cardboard or a VR headset, it will work in your browser, but you can sort of get a feel for what the telescope looks like. And also sort of a nice kind of outreach and teaching tool if you want to sort of take folks on a virtual tour there. So these are the receivers that we use, and in sort of radio astronomy lingo, which sort of inherited some of the World War II radar lingo. These bands are sort of named in a little bit of an arcane fashion, but these are the four main receivers that we're using right now at Green Bank: L band from 1 to 2 gigahertz, S band from 2 to 3, C from 4 to 8, and X from 8 to 12. I guess sort of the boundaries of these bands are a little bit sort of dependent on the telescope in question and the receiver in question, but that's sort of roughly how these bands split up. And so we're covering a wide range of the spectrum, in contrast to sort of some of the initial SETI surveys that were just done around the neutral hydrogen line, sort of the original experiments that Frank Drake did at Green Bank in the 1960s with a single tunable channel around 1420 megahertz. We're now covering essentially billions of channels at a time with the instruments that we have at Green Bank. So this is the infrastructure that we have there. Again, it's a bunch of sort of fast servers. This is actually just half of the cluster that's out there. So we have 64 of these compute nodes. It's nice because they're really just sort of scalable. If you want to add bandwidth, or if you want to deploy these to another site, you just spec one of these systems out, you put some hard drives in it, it connects up over commodity internet to just over Ethernet to a switch. And then you can stream the data to disk basically as fast as you can ingest it. So we're capable of digitizing 12 gigahertz of bandwidth. So this is really the most capable digital spectrometer on any radio telescope anywhere in the world, at least until our system at MeerKAT comes fully online. And right now at Green Bank, we have 8 petabytes of storage. So there's a lot of sort of storage capability, both for the initial raw data there, but then we can't possibly keep all of the raw data. We have to do this FFT and save the reduced waterfall plots that I showed you before. 400 teraflops of compute. There's 64 of these compute nodes, and each of them is writing the raw data rates of 750 megabytes per second per compute node. And again, we're observing 20% of the time. And so those raw data rates amount to hundreds of terabytes per day. And again, sort of doing a bit of the back of the envelope math, you can see that we would fill up the storage there very quickly if we didn't reduce those through this FFT process to dynamic spectra, which occupy more like a few hundred gigabytes per hour of observing time. So when we do that FFT, you make some choices in terms of the FFT length, which then determines the frequency resolution that you get. And then, of course, the time resolution as well, set by the uncertainty principle. Ultimately, you can't have arbitrarily high frequency and time resolution. So we actually do a little bit of averaging in time for the high frequency resolution data product. We get 3 hertz frequency resolution, and then we bin a little bit in time, and we get an 18-second sample time. But we can also take that same raw data, change the FFT length, and get more like an astrophysical spectral line data product out. Our sort of standard for that is 3 kilohertz frequency resolution, 1 second sample time. So if you want to look for galactic H1 or other spectral lines, then this is sort of the kind of data product that you want to use. And then we also have a pulsar data product with much coarser frequency resolution, but with a fine time resolution, which enables you to study pulsars or fast radio bursts. And so one of the other real sort of secondary science areas that's been really helped out by the instrumentation that we have at Green Bank is the study of FRBs, and we've had a number of external collaborators who've come in and use the instrument to look at FRBs and to get more data on them, particularly over the wide frequency range that we can provide. So this is an example of one of the waterfall plots from one of those compute nodes. So again, 64 of these nodes at Green Bank. This is the output from one of the nodes. Again, a waterfall plot where this time you're seeing 187.5 megahertz instantaneously of bandwidth. You're seeing 5 minutes of time on the vertical axis here. And then you're seeing these vertical lines, the straight lines here are the coarse channelization. And so we have a filter bank basically that channelizes these into roughly 3 megahertz coarse channels. And then there's a fine channelization step that gets us that 3 hertz resolution ultimately. And We have some software that just enables you to load these files in, so you can load them into Python as a NumPy array, and then your job is basically to find signals in these. And sort of if you're a classical radio astronomy, you want to get rid of the signals, you want to flag them, you want to get rid of radio frequency interference. We want to be a little bit more subtle here because we don't want to sort of throw the baby out with the bathwater. We want to actually detect and classify these signals and see if there's anything interesting in there. And you can see in this plot, there are sort of some squiggles that are in there in addition to just the sort of overall background bandpass shape. There's some signals that are sort of coming and going during the course of the observation. And so, the next step really is to figure out what those are. The problem with any SETI search is that if we were to put a telescope on the far side of the moon, where it's sheltered by a few thousand kilometers of rock from all of the radio emission that's coming from Earth, then the problem will be relatively easy. In contrast, here on the Earth, because we're not just in this protected band, and even the protected band of 1420 megahertz around the neutral hydrogen line is not maybe as protected as you would think. We do actually see some interference there, maybe some signals that get aliased into that band from elsewhere. But as you're expanding these bands out to cover sort of other regions of the spectrum that have been allocated to other uses, there's a whole bunch of radio frequency interference or RFI that you're going to pick up at those frequencies that you have to deal with. Even in the National Radio Quiet Zone, so there's a sort of federally protected area around Green Bank where there's restrictions on fixed transmitters, there's restrictions near the telescope on things like Wi-Fi. None of the staff on site have cell phones, or at least they don't have them active when they're at the site. So even though the environment is sort of somewhat shielded from cell phones, things like garage door openers, Wi-Fi, infamously things like microwaves, which caused some consternation at Parkes telescope a few years back. Won't sort of dig into that here, but again, sort of trying to reject these local interfering signals and make sure that they're not getting confused from signals that are actually coming from the sky is challenging. But even there, you're still going to have satellites going overhead. And so one of the things that we need to do basically is to discriminate in terms of the direction that the signals are coming. So this is another waterfall plot, another 5-minute scan, but instead of pointed at this particular star, Hipparcos 93805, we're pointed a degree away from the star, and we're taking another spectrum here. And then you can do these on-off observations. So this is a little animation. Hopefully this will work from the Stellarium planetarium software, pretty cool free software that you can use for all sorts of things. Again, I think this is a great teaching tool. But what I've done here is basically sort of simulated some observations where we're pointing the telescope at the star Vega for 5 minutes, and then we're going to point the telescope away. We're going to point back at Vega, away, back at Vega, and away again. So we're doing these sort of on-off observations, and you'll see as the star moves across the sky how the telescope scans, but you'll also see I'm plotting here the motions of some satellites across the sky. So hopefully this is going to work. You see the satellites moving. We're looking at Vega. We're looking away from Vega at a different star. We're looking back at Vega, and then we're looking away again and doing this 5-minute on-off cadence. Now we scan across to, here's Scion, and you can see here the geosynchronous belt. And so there's some satellites that appear stationary on the sky as viewed from Green Bank, but you can see that because the stars are moving relative to the geostationary satellites, it's unlikely that you're going to land on the same satellite as you're doing this on-off cadence. And so we can use this to attempt to isolate signals that are just coming from the target star. So in this case, you'd be doing scans of Scion, and you're looking for things that are in just those scans when you're on target, that are not in the scans when you're off target. And so this is what this looks like when you actually sort of look again just at the 187.5 megahertz of the data. So we point at the target, we point away, at the target, away, at the target, and away again. And then your job basically is just to find signals that appear in the top row of these scans that are absent in the bottom row. So the spatial filter then acts to hopefully localize signals that are coming from a particular direction on the sky, or at least to throw out signals that obviously are present regardless of where you're pointing. And if you look over in the right panel here, you'll see there's an obvious signal around 2400 megahertz that appears both in the top plot and in the bottom plot. So whether we're pointed at the target star or away. And to 2.4 gigahertz. This is a common frequency that's used particularly for Wi-Fi, and so this is likely a Wi-Fi signal, maybe from some visitor to the Green Bank telescope who hasn't turned off their cell phone, and we're picking up the Wi-Fi transmission here. So even again, at these sort of radio quiet sites, there's a lot of interference that you have to deal with and excise. You know, I've sort of put a cartoon signal here in the top row, you know, something that we would like to see. If, I doubt it would be sort of a pictogram like this, but if there's some signal that was just coming in on the top row that is not on the bottom row, particularly if that signal looks anomalous, then it's something that is interesting to us for follow-up. And meanwhile, we'd like to be able to sort of draw boxes around other signals in these plots, identify what they are, and excise them. And there's some techniques that we can use that are being developed, including modulation classification using machine learning, where algorithms have been trained on particular examples of different modulations. So I mentioned FM, but you know, there's other kinds of signals here with different modulations, and hopefully we can get to the stage where we can actually run these algorithms in real time and do this real-time interference rejection, which I think is also sort of interesting for other areas of radio astronomy that want to deal with RFI here. So another method that we can use is, of course, the well-known Doppler shift, which I'm sure all of you are familiar with. So the here with sort of an ambulance that's driving directly towards you, you get a Doppler shift and just a change in the frequency akin to, you know, the redshift of the galaxy. But then if you imagine an ambulance that is accelerating or moving at some angle to you, in addition to that Doppler shift, you also get a Doppler drift. So that's the next order, basically the change in frequency over time, which you would expect from a transmitter that's on a rotating planet and is being picked up by a telescope that's on a rotating planet. And so here is a little sort of you know, cartoon of how this works, again with the Green Bank telescope and Parkes telescope on our rotating planet Earth, looking for signals that are coming from rotating planets that are going around other stars. And a grad student, Sophia Sheikh, working with us, who was an undergraduate intern with us in 2016, had a paper recently in FJ that was just considering what range of drift rates might we expect just from what we know about the rotations of planets and the motions of planets around stars and the rotation of the Earth. And so this then sort of defines basically what is a reasonable drift rate range over which you should search how many hertz per second should these signals be drifting. And so we can do these searches basically sort of again in a sort of cartoon of the spectrogram here, where you have frequency on the horizontal axis and time on the vertical axis. I've sort of filled out some of the squares here as you would expect from a signal that is drifting at 2 hertz per second. In order to detect that signal, we basically just do some trial drift rate corrections here. This is also sort of similar to how pulsars and FRBs are detected using dedispersion, although here we're de-drifting rather than dedispersing. So you can do a trial of 1 hertz per second and then just add up the vertical lines here, and you see the numbers at the bottom here and just counting up the red squares. So that's sort of higher signal to noise than we were getting initially, now that we've done this sort of 1 hertz per second shift. And then I can do a shift of 2 hertz per second and add up, and now I'm getting sort of a maximum signal to noise, these 2 columns that are adding up to 7 down at the bottom here. And so in this cartoon example, by de-drifting at 2 hertz per second, I've corrected appropriately for the intrinsic drift rate of this signal that was drifting at 2 hertz per second. And so this is another filter. So in addition to the spatial filter in terms of localizing the direction of the source on the sky, we use this Doppler drift filter to look for narrowband signals that apparently are in motion relative to the telescope. And so this helps us get rid of a lot of that local RFI that tends to be constant in frequency, or at least not sort of drifting in a well-defined way that we can get rid of with these kind of techniques. So there's some software called TurboSeti that we can run that does these Doppler drift corrections and then outputs various hits that it finds and the associated signal to noise and the frequency at which it detected them. This is an example of actually some scans that we did with MWA, where it's actually a really nice RFI environment there. It's sort of very clean, even compared to what we see at Green Bank in terms of the interference that's present in those bands. So there's not many signals that we have to deal with, which is great. So you can do this search, again, now we're sort of stacking up these on-off plots. So we call these cadences, these scans of 3 on scans interspersed with 3 off scans. So these cadences of 6 scans. And you see here some examples of some Doppler drifting signals that were picked up in the on scans, that were absent in the off scans, then reacquired in the on scan, absent in the off scan, back in the on scan, and absent in the off scan again. And so this is sort of what we would expect by and large for a candidate SETI signal. It's a narrowband Doppler drifting signal that only is appearing when we're pointed in the direction of the star. We don't think that these are really very good technosignature candidates, in part because if you look at the frequency of these, they're all around 1380 megahertz, which is a frequency at which we see a lot of interference. And they're also, we're picking these up from various stars in various directions on the sky. And so this is sort of some kind of pernicious local interference that is has some sort of duty cycle that is turning on and off roughly with a sort of 5-minute cadence, and so it sort of fools both of these filters and looks like these potential sorts of signals that we might be looking for. But it really, these filters do help us get down from sort of an initial really sort of millions of hits that we get in these searches down to just a handful that can be looked at and gone through by eye. And then potentially we can follow up any that look particularly interesting. But it's still sort of a needle in a haystack problem. We don't know if there are any needles in the haystack. We don't know what the needles look like, if they are there. But we can do, certain searches. If you search through a certain amount of pay and you find no needles, then you can put meaningful upper limits on how many might be there in the remainder of the haystack. But there's a lot of dimensions of the haystack to search, and so we can sort of make choices similarly to what you would do in radio transient searches in terms of whether you want to push in spatial resolution, whether you want to push field of view, sensitivity, the overall bandwidth that you're covering, whether you're looking at polarization, how high your temporal and frequency resolution are. And then in particular, again, something that I sort of hinted at already, the data processing, the signal recognition, whether we can bring machine learning to bear on some of these problems as well. So at the launch of Breakthrough Listen, the sponsor, Yuri Milner, said he wanted to bring a Silicon Valley approach to the search for extraterrestrial intelligence, and we've sort of been scratching our heads about what does the Silicon Valley approach mean? Well, if you go to Google and you type in ET, they've got pretty good at delivering pictures of ET to you, including my favorite down in the bottom right there, ET dressed as Mr. T. So, they're pretty good at actually training algorithms. This is sort of powered by machine learning algorithms in particular that have been fed labeled data. So they have labeled examples of pictures of ET, and then they can go out and find more examples and return them to you. And so we want to sort of train an algorithm that obviously is not picking up, JPEG images like this, but is actually picking up things that look like candidates. And so, as Andrew, our director, said, we really want to build an anomaly detector or a serendipity machine. We have some initial work by a grad student who's now gone to work in industry, Jerry Zhang. You can go and look at this blog post or his papers that go into this, where he's training something known as a convolutional LSTM, long short-term memory. This is an algorithm basically that is sort of trained to look at the time evolution of the signals. And you see on the left here, in these sort of 5 images on the left of this plot, these are examples of real on-off scans. And so again, these sort of single waterfall plot where we're looking at the target, and then a second waterfall plot where we're off. And rather than sort of the full cadence of 6 here, where we're doing 3 pairs of on-off, these are just 5 separate individual pairs, these on-off scans. And you can see, for example, taking the middle panel here, these sort of diagonal lines that they were seen in the on observation, and there's a black line in the center there, and then in the off observation, those diagonal lines continue. So that's probably a local interfering source rather than something that is coming from the direction that the telescope is pointed in. In that same center panel, but now on the right, you see again these diagonal lines. The top of the 2 here is the same image, the same scan, and then the bottom is actually generated by by a generative adversarial network. And so this is a machine learning algorithm that has been trained on the data as a whole to predict, okay, you've seen this signal, what ought you to see next? And it predicts quite well what's seen in the left panel. And so, again, so looking at these 5 examples, if you look at the left-hand panel, set of panels, the top scan is the real data, and the bottom scan is real data on the off-target. And then on the right-hand side, the top scan is real data, and the bottom scan is what the algorithm thinks you ought to be seeing in the off-target scan. And so in the 4th example here, you'll see a narrowband signal that appears in the target and then is absent in the off-target position. But the algorithm that Jerry had trained here on the right thinks that that signal should continue. It predicts that that narrowband signal will still be present in the off-scan, and it's not in the real data. And so this is an example of an anomaly, and the kind of thing that we would like to really flag and say this one didn't behave as we thought it should do, given all of the other examples that are out there in the data set. So again, this is sort of something that's interesting, really sort of more generally from an anomaly detection perspective, could be applied to additional kinds of data. And we actually have, any of you that are familiar with Kaggle, this is a data science platform where sort of competitions are put out there for the general public to, or certainly the sort of expert public, to work their way through these data challenges and to come up with better solutions. And we have a Kaggle challenge that's coming up with the folks at Kaggle with some cash prizes for building better anomaly detection algorithms that are going to help with this issue. We have a bunch of public data that's out there. There's about 2 petabytes of public data, both these waterfall plots, the spectrograms, and also some raw data that is on our open data archive, including some scans of the Voyager 1 spacecraft. And so again, this is sort of, I think, just cool as a sort of teaching tool about how radio telescopes work, really. The fact that we can pick up Voyager 1 clearly with the Green Bank telescope, even though it's 20 billion kilometers from Earth, is just pretty cool on the face of it. But you can also work through these Jupyter notebooks, get some real data from the Green Bank telescope, process it through the Python software that we provide, and then extract the signal here. And again, there's a bunch of data that's out there that might be interesting for folks that want to do work on spectral lines, for example, folks that are interested in pulsars or FRBs as well. And again, I'd invite anyone that wants to discuss this to reach out and chat. So these are sort of the samples right now that we're focusing on with Green Bank. So there's about 1,200 nearby stars that are essentially complete at the 4 main receivers that we're using right now at Green Bank, in LSC and X, so 1 to 12 gigahertz. We also have several hundred targets from the TESS, Transiting Exoplanet Survey satellite catalog that we've observed. We're looking at the centers of nearby galaxies, and we're approaching completion certainly at the higher frequencies on those. And then we'll go back and do these sort of mosaic observations of larger galaxies as well. There's observations of the galactic center and the galactic plane. Again, sort of secondary science from this, particularly for the galactic center, is looking for pulsars close into the galactic center that could potentially provide tests of general relativity. There's a new sample that's out from theorist on our team, Brian Lackey, the so-called Exotica sample, where he's really trying to sort of come up with one of everything. I think this is an interesting paper just from the point of view of sort of thinking about classes of objects that are out there in the universe, and again, maybe sort of interesting to folks outside of SETI. And then there's observations of other targets, sort of targets of opportunity that we've looked at. And then I mentioned these sort of 4 receivers, but we're also starting to look at high frequency data from Green Bank as well. So I mentioned TESS. I had a summer intern working with me during the summer last year, Rafi Tras, who just had a paper submitted. This is out on the archive, where he's looking at a bunch of targets from TESS, again, using these 4 bands from 1 to 12 gigahertz with Green Bank. And this is sort of one of the key plots from the paper here. And so what you're seeing on the horizontal axis here basically is this EIRP, the equivalent isotropic radiated power. And so the sort of intrinsic power of a transmitter, if it were radiating in all directions, it might be beamed. There might be some sort of antenna gain basically here. But if it were beaming in all directions, what would the equivalent power of that transmitter be? And then in the vertical axis, this is the transmitter rate. And so essentially the number of transmitters, sort of an upper limit on the number of transmitters that might be out there. And if you've seen sort of radio transient plots, this is kind of akin to a rate sensitivity plot in radio transients, and that you really want to be moving sort of down towards the lower left of these kind of plots in order to get better sensitivity to transmitters that are more rare, basically. So if the volume density of the transmitters is lower, and if you also have additional sensitivity to them, then these points are going to move down towards the bottom left corner of the diagram. So Rafi's work is sort of similar in sensitivity to some of the other scans that have been done from these other sort of legacy surveys, including some from Breakthrough Listen. But it's nice because it expands out the range to a much wider range of frequencies, again, 1 to 12 gigahertz, and also is looking primarily at targets where we know that there are candidate exoplanets around these stars. So this is sort of just some recent work from the team that I think is quite nice, again, led by an undergraduate intern. I'm not going to really kind of dig into Parkes other than just to flash this up and say we're doing sort of similar stuff at Parkes, nearby stars, test targets, galactic center, and then exploring kind of new feeds at Parkes as well that are coming online. We also have, again, I mentioned sort of showed the map earlier on, ongoing collaboration with different observatories around the world, including Jodrell Bank, LOFAR, FAST Telescope in China, NenuFAR in France, Sardinia Radio Telescope, Giant Midwave Radio Telescope in India. And so there's a lot of different instruments that are really kind of joining the SETI search. Some of these are going to be operating commensally, again, sort of having our backends on there that are taking data at the same time as primary science users, so we're not actually ever pointing the telescope. And then, again, I mentioned LOFAR and the node at MWA that's just started capturing some live data as well. And so it's a lot going on. And if you're working on some of these telescopes and are interested in exploring the capabilities of our backends, again, please check this. I mentioned Optical Study, so I talked about VERITAS, this gamma ray Cherenkov telescope. The Automated Planet Finder, we had another summer intern who has led some analysis of Spectra from the Automated Planet Finder. And then we just had funded with a collaboration with Anne-Marie Cody at the SETI Institute an anomaly search in TESS, light curves. So TESS, the Transiting Exoplanet Survey Satellite. We're processing these light curves and looking for ones that look weird in some form or another. And so this is interesting from a SETI perspective, but it's also interesting in terms of uncovering unusual astrophysical variability. And in particular, we're interested in transits of both artificial structures around stars, but also potentially things like exocomets, dust around stars. And so nice project that's just starting up with Anne-Marie and Daniel Giles, a postdoc working with us there at SETI Institute. Mentioned a bit about machine learning and about fast radio bursts. Don't really have time to sort of delve into fast radio bursts other than to say that there has been some really nice work that's been done, particularly by Vishal Gajar on our team and collaborators on looking at FRBs using our digital backend. We do have 50 hours per semester of community shared risk time at both Green Bank and Parkes. And so if you're interested in proposing to use the backend through the normal time allocation committee process, then you can do that. And there's some nice papers again out there that are using machine learning to actually detect additional FRBs that were not found using classical approaches by training the classifier to look for them in the data set that we got from Green Bank. Another thing that's been done recently, so this is just sort of the cartoon of the sensitivity of a radio telescope, and in particular, the Rayleigh criterion, which sets the size of the primary beam, which is pretty large at Green Bank. It's several arc minutes, even up at X-band. And so typically, if you're looking at something like the Hubble Deep Field, that's fitting in a single pixel at Green Bank. And so even though you might think that you're just pointed at a nearby star, you're actually getting all of these other stars and indeed galaxies in the background and sort of doing a SETI search that also includes those targets. So there was some nice work led by a master's student, Bart Schroker at Manchester recently, who used the Gaia catalog to essentially extend the Breakthrough Listen survey of nearby stars to more distant objects without actually doing any more observations, but just by taking into account these other objects in the field. And then I mentioned this Exotica sample. And so again, sort of there's a blog post and a link to this nice paper by Brian Lackey with this sort of variety of objects in the universe, including, you see here, Oumuamua, the interstellar asteroid. We did do some scans of that recently. I guess for those of you sort of following the news closely, it's probably not a spaceship, but we do think that it is worth doing SETI surveys of unusual objects. You know, again, if we just sort of sit here and don't actually go out and do observations, then we're never really going to learn anything. And so doing these kind of searches, again, we think is sort of a key part, or should be a key part of astrobiology as a whole. I mentioned our internship program. So we've had about 90 interns since 2016. We're now an NSF REU site. Applications just closed for this summer, but I hope if you have students working with you or there are students on this call, you'll consider applying for next summer. And many of these students have gone on to grad school or gone on to careers in industry, have had first author papers. There's been, you know, really kind of a lot of nice stuff that's been coming out of this program. We provide pretty intensive training, including hands-on observations with Green Bank, doing the data analysis, coding skills, and it's been really exciting, particularly to see going on to grad school and sort of beginning to lead the field, a more diverse range of people, including a substantial number of women, a couple of women grad students who have been collaborating with us recently and leading projects that have come through our program and are now applying for postdocs. And so it's been great to sort of see that change in the demographics as well of the field. So again, you know, applications will open again in December for summer 2022. Just wanted to get an ad in for that. So, you know, just to wrap up, I think there's this nice quote from sort of one of the authors of this seminal paper, Packin and Murchison, in 1959, which really sort of launched the modern SETI field. We don't know. We're not sort of, I think as SETI scientists, particularly, you know, say I'm pretty sort of skeptical about our chances of success. I think it's hard to estimate our chances of actually making a detection. But we do know that if we never search, the chance of success is zero. And I would just add to that I think I don't know what our probability of success is, but given all the work that Breakthrough Listen is doing, we know that our chance of success is higher than it was 5 or 10 years ago. So I hope I've sort of given you a little bit of a flavor of what we're doing. You can see my email address there, and also our website and a tutorial about using our data. We have some social media platforms that you might want to follow us on as well. And I would be happy to take a few questions at this time. Thanks.
Thanks, Steve. We'll applaud for everybody. No, that was fantastic. I think we've got time for a couple of questions. I think people can just unmute and go ahead and ask.
Steve, sorry, it's Rick Gatescall here, faculty member. You mentioned far side of the moon. What do you think the time scale for conducting searches there, and do you think it actually will it give you the performance boost that could make a real difference, you know, over on the 50-year view, or do you think actually fairly sophisticated, coherent, synthetic aperture and more advanced algorithms are actually going to give you the real boost as Earth-based?
Yeah, it's a great question. I mean, I think we should be doing both.
Well, right. No, we're all in that situation. No, I mean, how much of an edge do you think it would give you getting onto the backside of the moon?
I think right now it would be great. I think the problem is that when the costs come down to the point at which we'll be able to build radio telescopes there, then there's probably going to be astronauts and sort of, cell phone networks and,
yes.
Wi-Fi and whatever up there as well. So I am a little bit concerned that sort of, we're going to kind of, put something there that then gets plagued by the same problems that we have on Earth. But there's a lot of folks that are looking into this. I mean, for EOR experiments as well. And so I know there's Jack Burns, who's been looking at some EOR experiments on the far side of the moon. The other example, or the other advantage being as well, that you can get to lower frequencies that are blocked by Earth's ionosphere if you're on the far side of the moon. And I think, there's some interesting stuff going on. I learned the other day that, Elon Musk's Starship, I mean, you don't know sort of how much to trust of what Elon Musk claims he's going to do and when he's going to do it, but he certainly is sort of shaking up the industry, and he thinks he's going to be able to get stuff to the moon at sort of $30 per kilogram, which sounds kind of incredible, but then that really sort of opens up some possibilities for sort of substantial infrastructure that you could build. I think that's on the near side, so probably more on the far side. But
yeah, no, I know people say he always promises a lot, but actually their record is quite impressive. They, critically, they've changed the sort of paradigm for rocket launching.
Yeah.
Therefore, this two order of magnitude reduction in cost per kilo, I think, is looking realistic. Yeah. So you're sorry. So I mean, assuming you can get isolation, we stick all the busy stuff on the near side and put the radio quiet stuff on the far side. Would it actually generate? But would it generate a significant many order of magnitude push in our ability to search for the electromagnetic spectrum? Do you think? I mean, how substantial antenna do you have to get there to really? Sorry, I've forgotten the sort of figures of merit. I know it's very difficult to estimate probability of success in this game, but because of the way things scale with volume, right? If you push out an R, you're fighting the 1 over R squared, obviously, of the noise, but you're embracing an R cubed volume. And therefore things can get exciting, should we say, in terms of the quantity of our galaxy that you're able to look through.
Yeah, so I mean, I think you would sort of start with a low frequency array, and maybe it would sort of look something like MWA, in terms of sort of a bunch of dipoles, or maybe even something that's kind of just printed on some substrate that you take up there in rolls and sort of roll it out. And I think if you, again, could sort of do something that's kind of fairly lightweight, sort of, fairly sparse array up there with a similar collecting area to some of these instruments on Earth, then you get a significant advantage over the Earth-based telescopes that, again, are having to contend with RFI and with the ionosphere. I think sort of for the higher frequencies, I mean, we're not getting, the GBT on the moon anytime soon, and the technology is still sort of in its infancy in terms of building aperture arrays at the higher frequencies. But, I think it's interesting. It's interesting to sort of at least keep this in mind. I think sort of our major push still for the time being is going to be taking advantage of the fact that the tech industry has these amazing machine learning tools that even as sort of we get more and more RFI and more regions of the band that are kind of almost unusable, we can still be sort of flexible and kind of, dodge that to an extent and kind of pick up things that are interesting.
Yeah, thank you.
Yeah, that's a question.
Any other questions? Okay, well, we're about to hit 1 o'clock, so I won't indulge myself and just say thanks again, Steve. That was great, and thanks for taking the time to visit us.
Thanks, and again, please do reach out if you have ideas about collaborations, either sort of interesting data sets that you think are worth exploring from a SETI perspective, or if any of the sort of instrumentation that I've discussed today sounds interesting for your science or the public data sets that we have. And again, appreciate the invitation.